This lesson is about solving polynomial inequalities. Already this semester, we've solved linear inequalities and absolute value inequalities. But the polynomial inequalities we're going to solve in this lesson are going to be degree 2 or higher. They're going to look something like this. Remember, the degree is 2 because that's the highest power of x we see. Solving these things will be more complicated than solving the linear inequalities we did at the start of the semester. We'll follow these 5 steps, so it's important that you learn the steps. And as I do the next 2 problems, you'll see me work each problem out each step at a time. So here's example number 1. We're supposed to use algebra to solve 5x plus 6 less than x squared and use interval notation to write our answer. So we can tell it's an inequality because of the less than sign, and it's not linear because of the x squared, so we're going to go through these 5 steps. Notice the first step. It says rewrite the inequality to get 0 on the right-hand side. Okay, that's easy. We're going to subtract x squared from each side. This will give us this inequality. While there's nothing wrong with this, it'd be kind of nice if our x squared term were positive x squared instead of negative x squared. And we can make this change if we multiply each side of the inequality by -1. But then notice, whenever you multiply each side of an inequality by a negative number, you have to reverse the inequality symbol. One last thing before we leave step 1. Notice, never divide each side of an inequality by a variable or take the square root or cube root of each side of an inequality. If you do, the problem just blows up. You'll get the wrong answer. Now for step 2. It says we're supposed to treat the polynomial on the left-hand side as a function and determine its set of real zeros. For it to be a function, it has to have both an input variable x and an output variable y. So I'm going to write it here as y equals x squared minus 5x minus 6. Now remember, the zeros of a function are the inputs that make the output equal to 0. So we're going to set y equal to 0 and solve for x. To solve this quadratic equation, I'm going to try to factor it. We need a sum of -5 and a product of 1 times -6. The numbers that I need are -6 and 1, because -6 plus 1 is -5, -6 times 1 is -6. Also, because a is equal to 1, we can use the shortcut, which allows us to factor this trinomial right away as this. Now we use the zero product rule. We have 2 factors, x minus 6 and x plus 1, and their product is 0, so I set each factor equal to 0. This gives me 2 simple equations to solve, so I come up with x equals 6 and x equals -1. These are the zeros of the function. Now we're ready for the third step. Use the zeros to form subintervals where the polynomial function will either be positive or negative. It's easy to do this if you put the zeros on a number line. These 2 numbers split the number line up into 3 subintervals. And now for step 4. For each interval, we pick a test input and calculate the associated output of the polynomial. And then we'll write down whether that's a positive or a negative output. So this first column is important. It explains all the entries in the table. For the first interval, I'll pick a test input of x equals -2. I could have chosen anything less than -1. -2 just seemed like an easy number to choose. For the middle interval, I'll choose x equals 0. 0 is between -1 and 6, and again, it's an easy number to work with. For the last interval, I'll pick x equals 7. Now for each of these x values, I need to plug the numbers into the function here and find out what y is equal to. This is a good time to use your calculator. And you might remember in class on Monday, we used the table feature of graphing calculators to speed up the process. The last part of the table is to make a note of whether y, the output, is positive or negative. So this first y here, 8, is positive, so we write y greater than 0. And the second one, y is equal to -6, well, y is less than 0, that's a negative number. And the last one is y is greater than 0. What we've just created here is sometimes called an interval chart or a sign chart. Now we're ready to write our answer. That's what step 5 says, write the solution set. But we need to think a little bit about this. We've done all the work, but we have to make sense of it. Notice our inequality here. The x squared minus 5x minus 6, that's the same thing as y. So what we're really looking for is y greater than 0. So check our interval chart. What are the intervals where when we picked an x gave us a y greater than 0? Well, the first interval did, and so did the last one. So we need to include these two intervals in our answer. So the solution set is going to be the union of these two intervals. So if we pick an x that's smaller than -1 and plug it in for x into our original inequality, it makes it a true statement. And if we pick x is bigger than 6 and plug them into the x into our original inequality, it makes it a true statement. So we're done. But you can see there's a lot to doing these problems. You really need to know the steps and practice doing these problems. Now we're ready for example 2. It's a similar problem. Use algebra to solve this polynomial inequality. Notice though that this polynomial is in factored form, but that's okay. In some ways that just makes our problem a little easier to do. Now we're going to follow the 5 steps that I outlined above. You might want to print out the lesson file so that you can refer to the steps as I do the problem here. The first step is rewrite the inequality to get 0 on one side, but we already have 0 on one side, so we get to skip step 1. The second step is to treat the polynomial on the left-hand side as a function, so I'll write down y equals that polynomial. Step 3 says to find the zeros of this function, so we set y equal to 0 and solve for x. Since it's already factored, we set each factor equal to 0. Solving each equation separately, for example this first one, I'll divide each side by 2 and then take the cube root of each side. I get x equals 0. For the second equation, subtract 3 from each side, divide each side by 2, and I get x equals -3/2. And as for the last one, x minus 4 squared just means x minus 4 times x minus 4. I can set each of them equal to 0, and I get the same answer both times, 4. So this function has 3 zeros. Now we're ready for step 3. Put these 3 numbers on the number line. The numbers subdivide the number line up into 4 intervals. These are the intervals for our interval chart. Next, I pick test input values. So I'm going to choose x equals -2 because that's to the left of -3/2. And I'm going to pick x is -1 for the second interval, x is equal to 1 for the third interval, and x is equal to 5 for the last. Now we calculate the output values, and I'll use my calculator to compute the value of y for each of our chosen test inputs. Lastly, we need to write down the sign of y for each of our test inputs. So we have y greater than 0, y less than 0, y greater than 0, and y greater than 0. So we've completed our interval chart. Now we're ready for step 5. Looking at our original inequality, we can see that we want y to be less than or equal to 0. So we're only going to use this interval here because this is the only interval where y is less than 0. However, we have one other thing to worry about. Y is allowed to equal 0. And remember, the zeros are exactly the inputs x that make the y equal to 0. So the zeros are going to be solutions also. So our solution set has to include all of these numbers written together at once. What I'm going to do is I'm going to graph them on the number line. First, I'm graphing the numbers in the interval -3/2, 0. And then I'm going to put dots on the numbers 0, -3/2, and 4. And I want to write this now using interval notation. This interval here is written like this. I have to put square brackets around the -3/2 and 0 because those two numbers have been shaded in. They're part of the interval. And then 4 has to be included also. So I'm going to have to use a union symbol. And then to write a single number by itself, that's where we use set notation. So I use the curly braces around the 4. And that's the answer. Now there was a lot on this first page. You might want to go back and rewatch parts of the video. But now we're going to head to page 2. Now we're going to discuss an important connection between the signs of polynomial function outputs and the vertical position of their graphs. Remember that the set of zeros of a function correspond to the x-intercepts of the graph of the function. Also, we learned in lesson 7 that the function's output is positive over the same interval where the graph of the function is above the x-axis, and the function is negative where the graph of the function is below the x-axis. This is summarized in the rectangle here, And it's not new. Again, we discussed this in Lesson 7. So now let's turn to example 3. As we do the problem, you'll see the connection between the sign of the outputs of f and where the graph of f is either above or below the x-axis. Okay, part A asks us to find the zeros of the function. So we want to find the x's, the inputs that make the output equal to 0. So we set the function's output equal to 0, and here's the equation we have to solve. To solve a polynomial equation, we like to have 0 on one side, and we already do, so we need to factor the other side. There are no common factors that we can pull from each of the 4 terms, but since there are 4 terms, we can group the first 2 together and group the second 2 together and use the factoring by grouping technique. We can factor x squared out from the first set of parentheses and -3 from the second set. Be careful when you do. When we factor -3 from 12, it's -4. Now, since we have x minus 4 as a common binomial factor, we factor it out, and it leaves us with x squared minus 3. Notice as we factored this, it's important that each step is written as an equation. The equal 0 doesn't disappear. Now we're ready for the zero product rule. We have 2 factors. They're multiplied together to give us 0, so we can set each factor equal to 0. We solve each equation separately. Add 4 to each side of the first, we get x equals 4. And for the second, we add 3 to each side, and then take the square root of each side. Remember, it's important when you take the square root of each side in an equation to not forget the plus or minus that gets put in front of the square root of 3. So the zeros of f are the numbers 4, square root of 3, and negative square root of 3. Part B is next. Sometimes people are a little bewildered by how do you solve f of x greater than or equal to 0. But if you remember, f of x just equals this. So we replace the f of x symbol with the x to the third minus 4x squared minus 3x plus 12. So this just gives us a polynomial inequality to solve, just like we did on the problems on the previous page. So let's follow our 5 steps. We've already got 0 on the right-hand side. Step 2 says to treat the polynomial on the left-hand side as a function, but it was given that way, and we're supposed to find its zeros, and we already have. So what we did in part A is actually step 2 of our process. So we're really ready for step 3. We put our numbers on a number line, we form subintervals, and then we're going to create our interval chart. The next row is to write down our test inputs. To know what kind of numbers we can use, it might help to put negative square root of 3 and square root of 3 into our calculator and get a decimal approximation. This helps us see that an x such as -2 is okay for the first interval, and then 0 would be fine for the second interval, and then something between 1.7 and 4 for the third interval. 2 would be a good number to use, or 3, and then for the last interval I'll pick x equals 5. The next line is for our outputs, and I get these y values by taking the x's and plugging them into the function. F of -2 equals -6, f of 0 equals 12, f of 2 equals -2, and f of 5 equals 22. The last row of the interval chart is easy. The sign of y is going to be here less than 0, then greater than 0, then less than 0, then greater than 0. Now looking back at our original inequality, we want y to be greater than or equal to 0. So we're going to use the x's in these intervals, and we're also going to need to use the zeros of the function because of the equals. To help me write the solution set, I find that it helps me to graph the solutions on the number line first. So I'm going to graph the numbers for this interval and for this interval. And then also, since we have the equals, the zeros have to be included, so we put filled in dots on the 3 zeros. This helps me see that the solution set is this union of 2 intervals. Part C asks us to find the intervals for which f is negative. F is negative means f of x is less than 0. So we can use the same interval chart that we just got done doing in Part B. Now we're looking for where y is less than 0, which means these 2 intervals. So our answer is the interval from -infinity to negative square root of 3, and also the interval square root of 3 to 4. Notice we're not unioning these together. We're not coming up with a single solution set. Each interval is a set, and they want us to list the intervals. So we just write them down with a comma in between. To answer the last two parts, we need to be thinking about the graph of f. And we graphed functions like f back in lesson 18. F is a polynomial function, so its graph is smooth and continuous. The zeros are going to correspond to the x-intercepts. The fact that y is greater than 0 over this last interval is telling me that the graph of the function is rising to the right. And then for the third interval, notice that the y is less than 0. That just means between these two x-intercepts here and here, that the graph has to be below the x-axis. Y is less than 0 forces the point to be below the x-axis. For the second interval, the y is greater than 0. So between these two x-intercepts, the graph will be above the x-axis. And then finally, for this first interval, well, since the y is less than 0, that means the graph's end behavior is telling me that it's going to be heading down towards negative infinity. So since I just made a rough sketch of the graph of f, now it's easy to answer the questions in part D and E. So what are the intervals where f is above the x-axis? Well, we can see the graph is above the x-axis here, and then also here. So here are the intervals. Notice that these two intervals correspond to our interval chart where y is greater than 0. As for the last question, f is going to be on or below the x-axis where y is either equal to 0 or less than 0. We can see the graph is below the x-axis here and here, and those two intervals correspond to these intervals in our interval chart where y is less than 0. But when we list those intervals, we have to make sure we put brackets around the zeros. Well, that's it for this lesson. There was a lot here, and I see that I finished in about 17 minutes. One reason why is because I wasn't able to pause and let people ask questions. But remember, when you watch a video, you can always pause yourself, and you can even go back and watch certain little sections over to make sure you understand what I'm talking about. One more thing, I hope you'll send me emails if you have any feedback. If possible, I'll try to incorporate your suggestions to try to make the videos better in the future. Also, you can send me questions about the content, and then that way I can collect the questions and maybe post some answers on Pilot. Oh yes, try the problems at the end of the lesson. There's a couple pages of problems. Try those, and if you have questions, you can ask me, and perhaps I can create videos working those out. I also might try to come up with a sheet of worked out solutions or just the answers to the problems.